So we've got this very nice notation to calculate time-ordered correlators in the free theory. I wanted to try to give you a little bit of insight into where this rule comes from. So let's maybe call this where does the diagram notation come from? So I just want to give you a few comments to make it, to motivate the diagrams and to maybe make it a little bit clearer where they come from, okay? So what are we actually doing? Well, we've got a string of functional derivatives. So I'm going to be schematic in my discussion now. We just want to identify what are the main points. And when we can see the main points on their own, that'll make it clearer how this diagram notation is working. So what we are actually doing is we're calculating a string of functional derivatives on this exponential, and then we're eventually setting j is equal to 0. Now, the first thing that I want you to notice is that when we take derivatives of this exponential, we keep bringing down the exponent. So we land up differentiating the exponent. Now, if we do differentiate the exponent, what do we get? Well, if we take one derivative of the exponent, so let's say we take a delta j of x1, we'll have 1/2, we'll have an integral, and then we'll get jx gx1. So x is what we integrate over. The 1 index that the Green's function has inherited was because of the derivative with respect to j1. And then we've got plus plus g1x jx. So can you see that taking a single derivative of the exponent, sorry, let me write this a little better. So the thing that we're differentiating is 1/2 integral j g When we take this derivative, what do we get? We get this result over here. So this result that I just underlined in green, that is the result after taking one derivative with respect to j of the exponent. If we now take a second derivative, so we have a delta j2 acting on delta j1, which acted on the exponent, then what we get is 1/2. And now this derivative with respect to j2 removes the j in the expression that's underlined in green and turns the x label into a 2 label. So we get g21 plus g12, but we know g is symmetric, so this lands up just giving us g12. So the point is, if you had set j is equal to 0 into the first exponential, after taking one derivative, this vanishes. If j is equal to 0, this, however, is non-zero at j is equal to 0. So we must act with a pair of derivatives in order that when we act on the exponent, we get something that doesn't vanish, okay? So we must act with a pair of functional derivatives on the exponent to get something that doesn't vanish. But which pair we act with really doesn't matter. And when we're drawing the diagrams, so this diagram that's underlined in red, it tells us we'll pair the functional derivative at x1 with the functional derivative at x2, and pair the functional derivative at x3 with the functional derivative at x4. The term underlined in green is telling us to pair functional derivatives at x1 and x3, and to pair the functional derivatives at x2 and x4. So where do the diagrams come from? Well, we need to take the string of derivatives and act on z of j, which is this exponential. To get something that's non-zero, the functional derivatives must act in pairs, and the diagrams are just a very nice, convenient way to record how we are going to pair the functional derivatives. This is a very, very simple example of Feynman diagrams, but I wanted you to understand it. In interacting theory, they'll get a lot more complicated, but the idea is exactly the same. They are an extremely powerful notation that simplifies all calculations significantly. Okay, great. So now let's just see, where are we? Well, we're at the stage now where we can now turn to perhaps one of the most important questions that we want to answer. So key question to answer now. What have we learned? We've learned that the two-point function, so the time-ordered correlator of a product of two fields, is equal to the Green's function of x1, x2. And our key question to answer is this equation true? So is that equation really true? And this is not obvious by any means. If you think about this side of the equation, and you think about how this object is computed, it's computed using our creation annihilation operators, which are acting in Fock space. So to compute the left-hand side of the equation, you're really thinking about operators, Fock spaces, quantum mechanics. To compute the right side of the equation, you solve a differential equation, and this is obtained using path integrals. So let me say path integral quantization. It is not obvious at all that by solving a differential equation, we're going to reproduce what we got from the operator approach. And that's exactly the question that we want to turn to now. So to answer this question, we need to solve the following differential equation. We'll have d by dx mu, d by dx mu plus m squared. Then we'll have our Green's function g of x comma y, and this is equal to the four-dimensional Dirac delta of x minus y. So this is the equation that we want to solve now. And the first thing that we're going to do is we're going to make an observation about translational invariance. So translation invariance. That's what we're studying now, okay? So to do that, we're going to imagine making a change of variables. So we've got our variable x mu. Let's set this equal to x primed mu plus a mu. And there'll be an exactly analogous change of variables for y, which is that y mu is equal to y prime mu plus a mu. How are x and y, x and x prime related? By doing a translation, okay? So we are now studying translations, and we're going to work out a consequence of translation invariance. Okay, good. So now let's perform this change of variables. If we did perform this change of variables, what would happen to d by dx mu? Well, we can write this by the chain rule as dx primed alpha dx mu d by dx primed alpha. And remember, the alpha index is summed, so that this equality is because of the chain rule. In these equations for the change of variables, a mu is a constant, And what that means is if we differentiate x mu with respect to x prime mu, so look at this equation over here. Well, the derivative of a is going to be 0 because a is a constant. So dx prime alpha dx mu is simply going to give us a delta alpha mu d by dx prime alpha. So that if we now do the sum over alpha, we'll get d by dx primed mu. So d by dx mu simply becomes d by dx primed mu under the translation that we are considering. And that's because a is a constant. This wouldn't be true if a wasn't a constant. Then let's look at x mu minus y mu. What is this equal to? Well, that's x primed mu minus a mu minus y primed mu minus a mu. And what you can see, look at the a mu's. We've got a minus a mu minus minus a mu. So the a mu's cancel. And we simply land up with an x primed mu minus a y primed mu. So if we now rewrite our differential equation, we learn that d by dx primed mu, d by dx primed mu plus m squared acting on g of x primed mu plus a mu and y primed mu plus a mu is equal to the four-dimensional Dirac delta of x primed minus y primed. But look at this. The equation that we've got in the green box above is exactly the same as the equation that we've got in the green box below. You know, you can drop the primes. The primes are doing nothing. So if we just rename x prime to be x, you can see that these are exactly the same differential equations. So if I solve the green box above and get an answer, I'm going to get exactly the same function as I'll get by solving the green box below. So the conclusion from this analysis is that, let me change the color. The conclusion from this analysis is that g of x and y is equal to g of x plus a and y plus a for any constant a. So that means for any a mu, which is not a function of x mu. Okay, and the only place where it was important that this is not a function of x mu was when we changed the derivatives. So let's be clear, it's this step over here. Inside that blue box, that's where we needed to use this statement, that a mu is not a function of x mu. Okay, good. So in particular, we can choose, no problem with doing this, we can choose a mu to be equal to minus y mu. If we do that, we learn that g of x comma y is equal to the g of x minus y comma naught. And that means whatever g of x comma y is this function, it is actually only a function of x minus y. And this is a consequence of the fact that if we do a translation, x equal to x prime plus a, the differential equation that we've solved is invariant. The consequence of that is that the solution is a function only of x minus y. This is going to be an extremely important fact when we are solving this differential equation.